Yo, what's up, everybody? Got another recording here. Just want to get into what's known as adaptive immunity. You know, we've talked about in some of the previous videos about just what specific or non-specific immunity or innate immunity. And we talked about, what goes into having an immune system. And we spent a lot of time on the last video really getting into the details of non-specific immunity. So now we're going to talk about specific immunity, which is also known as adaptive immunity. And I think what I really want to do is I know that people aren't dumb and can read. So there's no need for me to sit back and try to go over every single little word because anybody can read that stuff. But what I really want to get into is I want to get into some very key concepts that are dealt with when concerning immunity, specifically adaptive immunity, because that's really key. One of the things that I need to make clear to everybody who's watching this is something that's a very simple fact. I'm probably going to harp on it a lot, and something that you really got to keep in mind. And that is the fact that the only way adaptive immunity can happen is if the cells that are responsible for adaptive immunity get exposed to the antigen that comes from that particular pathogenic organism. If you don't have exposure, then you don't get any immunity, plain and simple. And there's actually a strategic process to getting that exposure to actually occur. So what I'm going to do is I'm going to screen share from it, and we'll go to the notes, and I'm going to kind of talk us through what I really want to get into for today. And like I said before, remember that the entire time that you're looking at what I'm showing you, that you're remembering that, hey, these are things that have to get exposed. So typically I don't go over learning objectives. I pretty much figure that people can read this stuff on their own, but there's some things in these learning objectives that I want to point out to you. If you're studying this for my class, for someone else's class, for anyone's class, if you're in medical school and you're trying to get down some basic background information, these are things that you need to have a mastery of if you're going to ace any examination dealing with adaptive immunity. You got to understand what lymphocytes do in an immune response. And really, one of the things you got to remember is that there are a group of cells that are interacting with one another, and that interaction hopefully is going to lead to exposure and activation, and then to creating an active immunity. So you'll read textbooks, you'll listen to different people, they'll tell you different names and words, but really you got three phases going on. You got exposure, you have activation, and then you have an active immunity that is created from all of that. If you don't have all three of those things, then you will not have an immunity to a substance, period. I don't care how bright you are and how bright your cells are. If they don't do those three things, then you're pretty much SOL. So the lymphocytes involved in this, you need to understand the lymphocytes, the names of the lymphocytes, what those lymphocytes do. It's more than just trying to memorize a function of those lymphocytes. I can almost guarantee you every textbook will let you down in that respect. The textbook will define that lymphocyte. It will make it clear to you what that lymphocyte does, but that textbook cannot make you understand the integrated responses of those lymphocytes in this process. You have to figure that out yourself. For example, when you say T lymphocytes, that's an actual broad term because there are multiple types of T lymphocytes. So as you start to study and you learn, you find out, oh, they're helper T cells and there are cytotoxic T cells. They are not the same. They don't even remotely do the same things. Cytotoxic T cells can attack and destroy infected cells or abnormal cells, whereas helper T cells don't attack anything. They're more of the dispatch cell of the immune system. You need to know the difference between cell-mediated and humoral immunity. With cell-mediated immunity, oftentimes I refer to that as being cell-to-cell combat. Humoral immunity deals with long range combat. Cell to cell combat means that they're going to get up close and personal. It's kind of like Mortal Kombat. When you play Mortal Kombat, most of the characters on that game do some type of hand-to-hand combat with one another. It gets very violent, it gets pretty brutal, and it gets very physical. Whereas humoral immunity deals with long range. So there are a few characters on Mortal Kombat who have long range attacks. The thing that I think is funny is that if you're really going to get with it, there's only one or two characters that I can really think of that are on that game who have heat-seeking missiles. And humoral immunity is more like a heat-seeking missile, or a missile that has a signature lock on it, where it's locked on to a particular thing or person, and it won't go after anything else but that target. And that's humoral immunity. Long story short, cell-mediated immunity is when a cytotoxic T cell winds up coming into contact with an abnormal cell and destroys it physically. Humoral immunity is when your B cells convert into plasma cells, and then those plasma cells, or I should say not convert, let's use the word that you would see in the notes, activate. Your B cells would activate, and they would then turn into plasma cells, which would then release antibodies. And those antibodies would be floating around in body fluids freely, so that it could encounter those antigens wherever in the body they may be. Then you also got to understand what the heck is an antigen. For some of you who have had me in a class before, you've listened to some of my previous videos, you've heard me talk about an antigen. And an antigen is kind of like a cellular license plate. It's on the surface of that cell. That cell is marked. As a matter of fact, the cells of your body have antigens on them already. We call them self-antigens or like antigens. Every person has antigens on their cells in their body, and it lets their body's immune system know that that's self, that's like, that's me. But when you introduce some type of organism or some type of protein or cell marker that is not like, it's not self, those antigens are therefore considered the enemy. They are pathogenic. Those antigens, those cellular license plates, are how your body is allowed to identify what's supposed to be there and what's not supposed to be there. It's kind of like at work, I have a faculty parking sticker on my car. And so that faculty parking sticker allows the campus popo to know whether or not that car is supposed to be in that faculty parking space or not. If I didn't have that faculty sticker, then the campus popo would know to slap a ticket on the car. The same thing with an antigen. An antigen, it will let your cells know whether or not it's supposed to be there or not. And by having a foreign antigen, a pathogenic antigen, I guarantee you, your body will snap to a response, and that response may be an immune response. And that's when you see things happen like fever and inflammation and whatnot. You need to understand an MHC1 and MHC2 protein. These are molecules or proteins that appear on the surface of the cell membrane of a cell. Are both of these proteins used on all the same cells? No, they are not. The MHC1 protein is generally found on the surface of a regular cell that has been infected. An MHC2 protein is found on an antigen presenting cell that happens to be a pathogenic, not a pathogenic, I'm sorry, a phagocytic cell, an immune system cell, like a macrophage. They'll present an MHC2 protein, and they have different reasons for presenting these, although the end result is quite fascinating. So let's talk about some of these things that we've brought out in the learning objectives already. What I've talked about, if you are getting ready to take a test on immunity and you didn't follow what I was talking about, you really need to go back and study. When you're able to follow what I just finished saying, then that's when you know you've got a real good grasp on it. Let's talk about adaptive immunity. Adaptive immunity happens because an antigen showed up. Okay. That's a good thing because that means that the minute the spy has been acknowledged, security alarms are going to go off in the body and it's going to respond. And that's a good thing. You need that. That's a great thing. The bad news is that a pathogen has to be identified before it kicks in. So that means that that pathogen can hide in your body. It can kind of lay low in your body and try to outsmart your immune system as long as possible. Because as long as it doesn't get identified and as long as it's not exposed to the enemy, or not the enemy, as long as it's not exposed to you and your cells, then it's safe and your adaptive immunity won't kick in. Innate immunity, it functions regardless. So you have a barrier up. Your skin doesn't activate when it comes into contact with a pathogen. Your skin is a wall, whether there's a pathogen around or not. It definitely takes longer to respond than innate immunity. I mean, that's how you can get a 24-hour bug real quick. All you have to do is have some random pathogen come into contact with some type of cell that releases pyrogens. And the minute it sees it, it releases those pyrogens. And those pyrogens are very potent. Once they're released, your thermoregulatory center will kick in your hypothalamus. And before you know it, you've got a fever. It's pretty quick, pretty immediate. That's why food poisoning can kick in the way it can. So, adaptive immunity takes some time. It can take a few days. You can measure parts of it over hours at a time, but still, even with those hours, part of it, carrying out its due process can take days. Lymphocytes, along with the different chemicals that they release and the proteins such as antibodies, all of that is known as the immune response. So the immune response is when your lymphocytes and the antibodies and all the chemicals that they release form a process that ultimately allows you to be able to gain some type of immunity. And of course, it's considered the third line of the body's defense because it's completely internal. The first two lines, the first line of defense is like your skin and your mucous membranes. That's keeping stuff out of your body in the first place. The second line of defense is things like fevers and inflammation and complements, proteins like those, neutrophils, macrophages. But then if there's a pathogen that gets in there and really, gets past all of that, if he can be exposed, then you can create a third line of defense. And that third line of defense will actively be looking for that particular pathogen at all times. So I mentioned beforehand, you got two different branches of immunity. There's cell-mediated and humoral immunity. Cell-mediated, of course, is always dealing with T lymphocytes, specifically your cytotoxic T cells, and those guys have cell-to-cell combat going on, where humoral immunity is dealing with B sites and B cells. And B cells are the same thing as B lymphocytes. And they activate and they become plasma cells. And then they create antibodies, which antibodies are proteins. They're kind of like cellular handcuffs that are specifically designed to bind to very specific antigens. So if you've got some antibodies and you say, hey, check this out, I got some antibodies. I'm gonna throw these antibodies at these 5 pathogens. Well, what did you originally create those antibodies for? Because if those antibodies were not created for any of those 5 pathogens, then it doesn't matter how many of those antibodies you throw at them, they're not going to work. It's kind of like buying a tire. The tire itself was at the factory. They made that tire for a specific car. So when you get that tire home and you find out that it doesn't fit that car, you can't get mad at the tire in a tire shop. I mean, you ask for a tire that was going to fit was going to fit a Ford Taurus, but you have a Yukon truck at home. Well, that Taurus tire is not going to fit that Yukon truck. You should have paid close attention to that. And you might say, well, then I think that tires should just be able to stretch and fit on there. Sorry, that's not the way it works. Whatever purpose you made that original tire for, that's the wheel that it's going to fit. Same thing for antibody. Whatever antigen you made that antibody for, that is what that antibody will fit. Never again will it fit any other antigen, only the antigen that you made it for. So when we line up cell-mediated immunity beside humoral immunity and we look at its different characteristics, we mentioned before, T lymphocytes are what you find in cell-mediated immunity. B lymphocytes work with humoral immunity. They're effective against two different antigen situations, and this is very important. This is less of a fact and more of a clue. Well, it's a fact, but I mean, it's just more of a clue to you, to something to remember. Notice that in the box, in that table, it says cell-mediated immunity deals with antigens within cells, while humoral immunity is effective against antigens outside of the cell. All right, let me explain the difference. When a cytotoxic T cell encounters an infected cell, that cytotoxic T cell does not walk up to that infected cell and say, "Hi, cell, how are you doing?" And then the infected cell looks at him and goes, "Oh, I'm doing quite well. Gee whiz, infected cell, you look like you're sweating. You look like you're nervous. Is anything wrong?" "Oh, everything's just fine." No, there's no conversation that goes on. The cytotoxic T cell does not obtain an MRI machine or something, or a CAT scan, and takes a CAT scan of the cell to look inside to see what's going on inside the cell. He can't do that. Cytotoxic T cell cannot look inside the cell of your body, and you are made up of trillions of cells. So no, the cytotoxic T cell is not going to look inside of the cell to go and see what's going on inside of him. The only way the cytotoxic T cell can look inside of that cell, or better yet, the only way the cytotoxic T cell can know what's going on inside of that cell is if that cell leaves or displays a sign to tell any surrounding cytotoxic T cells that there is a problem. And so that sign that they use is that magical MHC1 protein that I was pointing out a couple of slides back. That MHC1 protein is displayed on the surface of the cell membrane of that infected cell. But guess what that protein contains? That protein contains a fragment, or it contains a fragment or a piece of the protein or antigen of that particular pathogen that has infected that cell. So what I'm saying is, let's say that a virus infects a cell. It's a normal body cell. The virus infects that cell. He then takes over a lot of the manufacturing organelles and processes inside that cell. And that virus now infiltrates the manufacturing code of that cell and forces that cell to now mass produce polypeptides and all this other stuff that it's going to use to make a massive army of viruses that it's going to release into your body and make you sick as a dog. So while this is happening to the cell is unable to fight back against the virus. So one of the things that the cell will do is the cell will take a fragment of one of these polypeptides, place it in an MHC1 protein, and attach that MHC protein to the surface of itself so that any cytotoxic T cells passing by can see it. And once that cytotoxic T cell identifies that antigen being displayed by that protein on the cell membrane of that now infected cell, then that marks it for deletion. Now the cytotoxic T cell understands that he needs to destroy that particular cell. However, that's what happens when the antigen is on the inside of the cell. usually when something's inside the cell hiding and destroying the cell from the inside out. Sometimes you have antigens floating around in your body fluids. For example, let's say that you've got some type of pathogen, some type of microorganism that's in your body tissues, in your body fluids. Let's say you got some type of bacteria that's made it into your body fluids, and that bacteria is wreaking havoc, reproducing itself, and destroying the surrounding tissues. And in that process, he's utilizing whatever nutrients you have in your body to use for himself. But on top of that, while he's using your nutrients, he's also expelling waste products in the form of what we call toxins. And those toxins are chemicals. However, when you look at it under a microscope and you break this down to more of a chemical level, those chemicals are nothing more than small molecules. And so after you come into contact with certain pathogens that are floating around in your body, sometimes you'll find out that those pathogens have certain antigens attached to them, or their product that they produce turns out to be the antigen that we're talking about, some foreign substance in the body. And so we'll make antibodies that can float throughout the body fluids, large quantities of these little handcuff molecules that can go out and arrest these antigens. Now, not hormones. These chemicals that we were just talking about, none of these chemicals are alive. So antibodies are not alive. All right. Even though I may talk about them like they're some cartoon character, antibodies are not alive. They are just floating around in the body fluids for set periods of time, and they ultimately come into contact with an antigen. They bind to the antigen and mark it for destruction and mark it for removal. Now, the next phase in that table is, does it require antigen presenting cells? Cell mediated immunity? Yes. A cell, a cytotoxic T cell cannot tell if that cell is infected or not unless that cell is displaying an antigen presenting protein. Whereas humoral immunity, no, it can make its antibodies directly in direct relationship to the antigens that are floating around in the body fluids outside of a cell, or for that particular pathogen itself. And then you can see here the antigen molecule structure. We'll talk about that in a separate video. And then the general effector response. Generally, what happens with cell-mediated immunity is there's a release of cytokines for activating other immune cells or for destroying infected cells. So what winds up happening is once the cytotoxic T cell finds an infected cell, the cytotoxic T cell is activated. And once it's activated, it can release cytokines, and then more cytotoxic T cells will activate. And then they'll begin to go around destroying more of the infected cells. Whereas with humoral immunity, the general effector response is actually when you stimulate the B cells activate, they become plasma cells, and then they create and then release antibodies. That's the end result that you get out of the humoral response. In the humoral response, you ultimately want to wind up with antibodies. If you don't wind up with antibodies at the end of the humoral response, you don't have immunity. It's plain and simple. You don't have antibodies, you don't have immunity. You got to have antibodies there because those guys are going to be there for the sole purpose of being able to attack these antigens the next time. They'll be there. They'll already be in body circulation. And because they'll already be in body circulation, they're already prepped and prepared. So if those antigens ever show up again, you may be able to shorten the amount of time that you feel the feelings of being sick. Okay, we talked about antigens. One thing I want to point out at the bottom of this slide is the fact that the immune system usually can distinguish itself from everything else. But when it can't tell itself from a foreign substance, this is when we refer to it as autoimmune disorders. In other words, the body is attacking itself. Remember, I said that normal cells inside of you and me have their own antigens. They're cellular license plates that are on the cell membrane of our cells. And we have antigens that are good antigens because those antigens are ours. They belong to us. The problem is when we come into contact with our own antigens and our body gets confused and it sees our own antigens and it thinks that our own antigens belong to someone else or they are not ours. And that really becomes something that's problematic. It can actually kill you. Okay, I wanted to skip ahead a little bit because I want to talk about T cells and B cells. Notice that here it says that they have about 100,000 unique receptor complexes and they bind to specific antigens. So you have to keep in mind that our body has the ability to be exposed to, hundreds of thousands of different things any given day. We have to have that because what you can't see is that you are exposed to hundreds of thousands of different things every single day. You just don't know it. You know you don't get sick around everything, but you are exposed to some of everything on any given day. B lymphocytes, they can make direct contact with an antigen. Okay. T lymphocytes, they have to have the antigen process. So the antigen has to be presented in the plasma membrane of another cell type, and then they're able to scan it. And then they got some extra receptor molecules that are on their cell surface to help them when they are interacting with the cell that happens to be presenting the antigen in the first place. So basically, B cells, they can come into direct contact with the antigen. So let's say there's this antigen floating around in the bloodstream, and a B cell comes into contact with it. As soon as it comes into contact with it, it will go ahead and activate. It'll go from B cell to plasma cell, and then poop, it creates antibodies, and those antibodies come out and they start attaching to that antigen and any other antigens around that those antibodies can find. The end. It's quick and dirty and done. T lymphocytes are different. T lymphocytes, they gotta, T lymphocytes are not floating around looking for the antigen outside of the cell. They're checking cells to see if that antigen has made it inside of a cell. And so that cell then has to process that particular antigen. It has to create an MHC1 protein. It has to put that antigen inside that protein, then float that little guy to the surface of its cell membrane and display it for the world to see. Let me talk about this just for a second, and then we're going to move on to some other slides. T cells and B cells, when you get further on in here, and we probably won't get a chance to talk about it in this video, but you'll read something about CD molecules, like a CD4 molecule. They are what we call coreceptors. Coreceptors are oftentimes utilized in conjunction with another particular plasma protein, not plasma protein, but cell membrane protein. There's probably a protein that's located on the surface of the cell membrane, and when it is activated, these coreceptors then kick in. And what winds up happening is you'll find that there are a lot of different coreceptors, but for the sake of adaptive immunity, you're going to find that these coreceptors, they help this immune cell to know friend from foe, and they kind of allow that immune cell to know what it needs to destroy and what it doesn't need to destroy. And now this is very important. And as you study further on, and like I said, I don't think we'll get to this in this particular video. And further along, you'll find that these coreceptors are actually used quite a bit, especially when a cytotoxic T cell or a macrophage has communications with a helper T cell. And when they had this communication with the helper T cell, that that's when good information can be passed along. But the only way that they can know that this is not an antigen presenting cell that I'm supposed to destroy, and that this is actually an antigen presenting cell that I'm supposed to actually talk to, is with these co-receptors. Two of the cells that you'll talk about anytime you're studying adaptive immunity, excuse me, as far as CD molecules, is a helper T cell, which has a CD4, and a cytotoxic T cell, which has a CD8. You'll notice that helper T cells have CD4s because they need to be able to go and talk to B cells and activate them. So, for example, let's say that a helper T cell comes into contact with some macrophage that just engulfed a pathogen. So this macrophage engulfs a pathogen. He takes a piece of the pathogen, which is an antigen, and presents it on his cell membrane, and then the helper T cell scans that. Well, it's going to scan that, and it's going to go have a chat with the nearest B cell that it can find. The CD4 molecule on its cell membrane allows it to be able to have those conversations. A CD8 on a cytotoxic T cell is what it allows it to be able to bind to the MHC protein located on a infected cell. It binds to it, it reads it, it understands that this cell that it just bound to is infected. The CD8 allows it to do that, and it allows the cytotoxic T cell to initiate the release of different toxic chemicals that will ultimately kill that infected cell, as well as the antigens on the inside. So let's skip ahead to MHC proteins, because we're starting to run out of time here and what we wanted to talk about. And this will kind of give you the intro to what's happening in an immune response. And we're going to look at 3 different images, and then that should wrap us up for this particular video. If you notice in the first video, this is labeled, not video, but slide. You'll notice that it's entitled Formation and Docking of MHC Molecules in a Healthy Cell. So what's happening here is, here's the cell membrane or the plasma membrane. There's the cell membrane of a normal cell. Down here, we have peptide fragments of self-antigen. In other words, this antigen belongs to this cell. It's his. It's kind of like my driver's license. You know, my driver's license would be a self-antigen. It's mine. It shows who I am. It is a picture of me. It really is me in that license. So this peptide fragment of self-antigen, notice that it's a peptide fragment. So it's not an entire peptide. It's not an entire protein itself. It is a piece of a peptide that's been broken off from something else inside the cell, placed in a membrane-bound bubble, which happens to be a transport vesicle. That transport vesicle, before we get to transport vesicle, let me back up. That peptide fragment here inside the ER, endoplasmic reticulum, this peptide fragment is then attached to a MHC1 molecule, which is this big surface protein. The self-antigen is attached to it, and then it's put into a transport vesicle. And of course, a transport vesicle has one purpose, that's to transport stuff. So it transports this complex, this MHC class 1 molecule with this peptide fragment, this self-antigen attached to it, and it transports it over here to the Golgi apparatus, aka the Golgi body. And the job of the Golgi apparatus is to be the UPS organelle of the cell. It packages things, it processes it, packages it, and ships it to wherever it wants to go. So this is the UPS organelle of the cell. It takes that transport vesicle, the transport vesicle opens up, it dumps out this MHC class 1 molecule that happens to have a peptide fragment of a self-antigen attached to it, and then it bundles it up into a secretory vesicle. Now, this is not a transport vesicle. This is a secretory vesicle because it's going to secrete it. Not to transport it, but secrete it. And that little vesicle floats out here to the cell membrane, and then it releases it onto the cell membrane. And then the cell membrane takes that MHC class 1 molecule along with the self-antigen that's attached, and then attaches it to the actual cell membrane so that the self-antigen is being presented on the outside of the cell. It does this so that that can become his license plate, so that every immune cell in the body recognizes this cell as this is mine. And I don't need to attack it because it's mine, because those are those self-presenting, those are self-antigens being presented on the cell membrane. That's its MO. That's its license plate. That's its driver's license. That's its ID tag. It's letting every immune cell in the body know, don't destroy me. I'm okay. There's nothing wrong. This is normal. However, you flip to the next slide, and the only thing that changes in that name now is this is what's happening in an unhealthy cell. Just like a healthy cell uses the same molecule to be able to tell the rest of the body that it is okay and that it is normal. A cell, once it's infected, will then in turn take that same MHC class 1 molecule, and instead of attaching a self-antigen to that MHC1 protein, it will attach a peptide fragment of a virus to that MHC1 protein and display that joker on the cell membrane, so that when a cytotoxic T cell comes by and it scans that cell, it will then read that particular MHC class 1 protein or molecule, and it will say, you know what? This foreign antigen is not supposed to be here. This is not a self antigen because I just read his other self antigens. But this thing sticking off of the cell membrane is a foreign antigen. And so therefore, this cell must be infected and I will destroy him. And you'll notice that the viral particles over here on the far left-hand side are very small. And that was something that I pointed out in a previous video. The fact that the size of these pathogens and the size or the characteristics of the pathogen will dictate what the pathogen can do and where it can go. A virus is a very, very, very tiny pathogen. So therefore, that pathogen can get inside of a cell and kind of hide in a cell. This particular virus, he wound up making his way into this cell, and you'll see that this cell released a proteasome, and the proteasome comes in and it helps, the proteasome helps to digest the protein of the viral particles, breaking it up into pieces. Now, this is all wonderful and great and everything. However, this is probably happening because the virus has already made his way. The viral particles have already made their way into the cell. We're seeing this one little membrane-bound bubble, but there's probably this virus has probably already made his way in and started his replication process inside the cell. So what happens is the minute the cell comes into contact with the viral particle, it goes ahead and it breaks it down and goes through the same process that our healthy cell did, except this time it's concerned about the fact that this is not a self-antigen. This is a viral antigen. And then once you get to understand that and the fact that a unhealthy cell cannot fight back. It's not going to fight back. It's going to be marked for deletion. It's going ahead and it's telling its friends, go ahead and destroy him because he's not going to make a comeback. Well, what happens to other cells? Let me go through this real quick. You'll notice that these are MHC class 2 molecules, okay? They provide means of communicating with helper T cells. So when we look at this image, what we're seeing is we're seeing the formation and docking of MHC class 2 molecules in a antigen presenting cell, like a dendritic cell that you will find in your skin, or a macrophage, Cookie Monster cells, or a B cell. All right. These are all cells that can engulf a pathogen or a microbe through phagocytosis. So here's something you need to get straight when you're looking at this particular slide. This bacterium that is getting attacked, this bacterium did not go into the cell. This particular cell engulfed that bacterium. All right. So this cell is not being invaded. In the previous slide, that cell was being invaded. In this slide, the cell is not being invaded. This cell is eating this bacterium. He brings him into a special membrane-bound bubble that bacterium will not be able to get out of. It's called a phagosome. And so he pulls him into this membrane-bound bubble, sticks him in there, and then what he winds up doing then is the cell starts processing an MHC class 2 molecule. He synthesizes it in the rough endoplasmic reticulum, transports it over in a transport vesicle over to the Golgi complex, and then he waits. And he waits there until he's released in a lysosome. Well, when he's released in that lysosome, that phagosome is floated over beside the lysosome, and then they get to know one another a little bit better. And so what winds up happening is they get to know one another better, all right? They destroy that pathogen that was on the inside. And in the process of that, they take a piece, a foreign antigen piece off of the bacterium. So it's kind of like blowing up a car, and then you go and you look at like a piece of the car and say, this is evidence. Well, that's what these foreign antigens are. They're evidence. They're pieces of evidence of what the actual threat happens to be. But they treat the evidence like the real thing. Okay? It's like I went on a trip several years ago with some guys to this deluxe cabin up in Tennessee, in the mountains of Tennessee. And we get up there, and we got there late that night. Well, we all arrived at different times. I got there late that night, and I was standing outside, just spending some time looking at the sky and everything, because it was one of those 3-story cabins, real nice. And one of the guys comes to the door and says, "Julian, I think you really need to come inside." I'm like, "Why?" He's like, "Dude, it doesn't look like it, but there's bears up here in the mountains, and it'll see you before you see it. Trust me, you want to come on inside. When the daytime comes and the sun comes up, you'll be able to go back outside, and I'll show you what I mean." Well, the next morning, I went outside and looked around the trash cans, and sure enough, there were these big bear paw prints where the bear had come through and was checking out all our cars and trucks and had gone through the trash to look to see if we had left anything outside. So when I saw those bear prints, that I didn't see the actual bear. I never saw a bear while I was there. That bear print was enough for me to know I need to be careful when I'm out here in these woods, because they are real live bears. The same thing for the foreign antigen. That foreign antigen is treated like the actual pathogen itself. It is evidence. So when that foreign antigen is attached to that MHC class 2 molecule, that thing is set on the cell membrane so that that particular APC, that antigen presenting cell, he can present it, and he can say, "Hey, everybody, look what I found. Look what I just beat up. Look what I just destroyed." And then you can see what I've got. And what's going to happen is a helper T cell is going to come alongside. Let me see. I hope this is the next slide. And then what you see here is a helper T cell. That's not the slide I was looking for. But what's going to happen is a helper T cell will come alongside, and it will bind to a complex that'll be created here. And when that helper T cell binds to it, it'll be able to read it, and then that helper T cell can then activate and tell other immune cells what it just found. Okay, that's where I wanted to stop for today. It gets a lot deeper after that. We're going to have to make a whole nother video for this, though. So had to find myself there for a minute. And so what we'll do is we'll come back in Later on, we'll have some other videos that we'll be able to display and be able to show you guys so you can see what's going on. Did anybody have any questions? Anybody have any questions? No questions? Great. Okay. So we'll come back in and we'll make some more videos in the near future. One of the things we want to talk about in the near future are the different types of antibodies, because the antibodies are very different. There's like 5 different groups of antibodies that we want to get through. We also want to talk about the antibody production process. And we kind of want to talk through one other thing. Before I get off, there's one more thing I want to throw at you, and that's everybody's probably waiting to hear about the flu shot. Okay, how does the flu shot work? We'll take some time to really get into detail of the flu shot later, but for your curiosity's sake, what I do want to point out to you about the flu shot is this. The flu shot is, we talk about the flu shot, and some people say that the flu shot prevents the flu, and all this, that, and the other. So I noticed that a lot of talk about it is kind of messing up people's understanding of what the flu shot happens to be. The flu shot its purpose is to give your body prior exposure so that you can establish some type of adaptive immunity before you come into contact with the actual flu virus itself. Usually what we do with the flu shot nowadays is we give you this little cocktail mixture of different viral strains. So we take a whole bunch of viruses, all the viruses are dead, they've been inactivated, we mix it together and we give it to you in a shot. Your body's adaptive immune cells, they in turn become exposed to these antigens that we just injected you with. The good news is that what we just injected you with is either dead or innate, not innate, but immobilized. They don't work. So when you go get the flu shot, don't freak out. We're not giving you a live virus or an activated virus that's going to, go and run roughshod all through your body. We're just kind of hoping that your immune system will be able to, create a defense for itself after playing with these crash test dummies. So it's kind of like going on a firing range and shooting at some targets that don't shoot back. You get all the training you need, you get all the practice you need, you get used to firing the gun, all without someone shooting back at you. But that's the only benefit. So can you get sick off of the flu shot? Sure, because your body is going to have an immune response, and so if these antigens are found by other cells in your body that release cytokines and specifically like pyrogens, then you can get sick.
So y'all sent me an email and needed to get to the